record. Hello, everybody, and thank you for joining for our next scientific online lecture at the Ipanema. It will be given by Roberta Menezes from Tech, and she will tell us about Flexdym polymer for biotech applications and device commercialization. So thank you, Roberta, very much, and the floor is yours.
Hello, Ivana. Thank you so much for having me give this presentation for the Ipanema Scientific Online Lectures. So my name is Roberta, and I'm Chief of Marketing and Sales at Tech. Essentially, what we do is develop microfluidic, user-friendly microfluidic tools for the development of microfluidic technologies. And today I am going to be talking to you about our Flexdym polymer that has been designed specifically for biotechnology applications and device commercialization. So I'd just like to start off by highlighting the key topics I want to cover today. Firstly, I'm going to give you a little bit of a context and really highlight the key material challenges that are associated with the development of microfluidic biotechnologies. Then I'll present to you our Flexdym polymer and what are its key properties and advantages that give it an edge. Then I'll explain to you exactly how you can fabricate Flexdym devices for these biotech applications, followed by covering a key aspect of bonding and device assembly, which is really essential to the efficient and rapid production of microfluidic devices. And finally, I'll talk about two of the top biotech applications we currently observe using the Flexdym polymer. So if we have an overview of the polymer microfabrication process, you will see that there are 5 key steps. So you start with your device design, master mold fabrication, then device replication and assembly, and finally, if desired, mass production of your devices. But for the smooth and seamless progress of one step to the next through this fabrication process, really, you need to think about the materials that you're going to be using. And currently, the most popular materials that are used are, for example, SU in silicon wafers at the level of the master mold fabrication, and then 2 families of materials for device replication and assembly, which are PDMS and thermoplastics. So academics tend to flock to PDMS because it has several advantages. Firstly, it's optically transparent, it's also biocompatible, and it has relative ease of fabrication. But it also does possess some drawbacks. So it still remains expensive. The scale up is very complicated because the devices have to be manually assembled. And these protocols, although they're relatively easy to learn, they involve many laborious steps of mixing, degassing, and then the use of different clean room equipment. So it is far from optimal, let's say. So what tends to happen in industry is that innovators will select thermoplastics, which are highly advantageous for scaling up, but they have their disadvantages for prototyping because the process of mold fabrication can be expensive and complex. And also at the level of the device assembly, there are usually harsh chemical and temperature bonding treatments that are implemented. So here we have a highlight of what are really the key properties that a researcher will look for in a material when they want to develop a microfluidic technology for a biological application. We have optical transparency, deformation, permeability, hydrophilicity, which the last 3 are often linked to, for example, cell culture. Optical transparency is going to be linked to your fluorescence microscopy analysis. And then obviously biocompatibility is a given for all of these biological applications. But then we also have those properties that are linked to the device fabrication, so the production of the devices, their scalability, and their assembly. And although all of these materials possess advantages for different applications, most of them are going to have drawbacks when it comes to the device fabrication, production, and assembly. So for example, in the case of PDMS, we all know that we need to implement oxygen plasma treatment, which is not ideal for functionalized devices. And the same case goes for thermoplastics, which are going to implement those harsh temperature and chemical treatments that I previously mentioned. So there is not only a need for a material that will fulfill all of your biological and experimental requirements, but also one that will keep down the costs for the production and the assembly of the devices. So here we have a material that looks like PDMS. It's optically transparent, it's elastomeric, and it is easy to handle. But this is not PDMS. This is Flexdym, the polymer that we have developed. So Flexdym is a soft thermoplastic elastomer, which combines the best of elastomers like PDMS and thermoplastics like COC and polystyrene. It has a Young's modulus of 1.15 megapascal, which is in the range of PDMS, and an elongation of 720%. And this is all thanks to its block copolymer nature. So Flexdym is composed of diblocks and triblocks made of styrene hard blocks and ethylene butylene soft blocks. And these different components make it so that the material has two glass transition temperatures. So there's going to be one glass transition temperature that is negative, which will allow those polymeric chains of ethylene and butylene to remain in constant motion and give the material its soft elastomeric properties. And then it will also have a second glass transition temperature at around 100 degrees Celsius due to the styrenic blocks, which will give it the moldable aspects that you see with other thermoplastics like COC. And those styrenic blocks are going to act as anchors to the ethylene butylene polymeric chains that are in motion. So now we're just going to cover some of the key surface properties of the Flexdym. So firstly, Flexdym, what is interesting is that it has lower absorption properties than you would typically see with PDMS. For example, here in the image on the far left, what we can see are microscopy images of a straight microfluidic channel that has been incubated with a dirhodamine for 24 hours. And then what we do is we rinse this channel, and we can observe a typical effect for PDMS. I'm sure many of you have observed this before, that the dye is absorbed into the material. So you can still see that dye in there. But this result is completely avoided with the Flexdym because the Flexdym does not absorb the molecules in the same way as the PDMS. And not only that, the polymeric chains are not going to leach out into the media that is inside of the channel because of those styrenic blocks that act like anchors. We've also done tests to check that Flexdym is resistant to certain solvents that are commonly used in microfluidics. So for example, fluorinated oils that are used for droplet microfluidics, and acids, bases, methanol, ethanol. Now we do see some swelling for carboxylic acid and other oils, but this is typical of many of these materials that are used for microfabrication of microfluidic devices. Now, when it comes to the surface treatment, Flexdym, like many of these other materials, is moderately hydrophobic. However, it displays an incredible stability, hydrophilic stability, once it has been treated with oxygen plasma. And this can last anywhere from 1 week up to 1 month, depending on the specific storage conditions of the device. And then, like many other thermoplastics, such as COC, because Flexdym possesses these ethylene components to the material, it can be functionalized with commonly used amino-based EDC and HS coupling for functionalization of the device with DNA and protein. And sealant-based chemistry will also work as well. And we also have UVVis spectral data showing that Flexdym permits transmittance between 295 and 800 nanometer, which means that it is compatible with fluorescence microscopy analysis and works with the commonly used dyes, for example, such as Psi3 and Psi5. Now, Flexdym comes in different formats, and depending on that format, there will be a different microfabrication method implemented. So for example, we have Flexdym sheets and Flexdym pellets, which are already currently commercialized. And the Flexdym sheets, which are extremely easy to handle, are fabricated through a method of hot embossing. So for those of you who are mostly familiar with casting and PDMS soft lithography, I will explain in the next slide exactly how this method works. But the hot embossing method, what is important to know here is that it uses a hot press, and it can be implemented not only in the prototyping stages, but also when you want to mass produce your devices. So there's automated hot embossing that exists as well. And then the Flexdym pellets are really ideal for injection molding. So injection molding is the most commonly used microfabrication process for the mass production of microfluidic devices. And so we have created the pellets exactly for that purpose. And then we also have currently in our development pipeline, in the works, the preparation of 2 new formats of Flexdym. So Flexdym, which is a liquid format that will be used for the creation of more sophisticated features, for example, permeable membranes. And also we would like to create a more higher resistant version of the Flexdym that's going to be resistant to different solvents. And this, we call it FluoroFlex, but these 2 are just in the pipeline for the moment. So I'm going to go back to the Flexdym sheets and the hot embossing process for creating your microfluidic chips. So here what we have on the left is our hot embossing machine called a Sublime, but there are classic hot presses which will function in a very similar way and for which you can use the hot embossing. And if we look at the image on the top right, what you see are the key steps of the hot embossing process. So we have a mold which possesses your microfluidic features, your channels and chambers, the Flexdym sheet, which is symbolized in blue, and then a counter mold, which has a smooth finishing just to make sure that you have that pristine, transparent finishing for your sheet on the other side. And what we will do is apply pressure, heat, and use time to then transfer those micron features from the mold onto the Flexdym sheets. And this is how you can create your molded Flexdym sheet for your microfluidic device. And this can be done essentially in a matter of a few minutes. So it is really a practical method that does not involve many steps. There's no preempted mixing steps, and you can have your molded material essentially straight away. But what is key to remember is that the mold that you're going to be using is very important. So here I have a selection of molds, which are molds that can be used for hot embossing. So the ones that you might be the most familiar with are the SU8 and silicon wafer molds that are used in PDMS soft lithography. However, these molds, because of the SU8 features, what tends to happen is that those features can be easily damaged. And this is something you see when you're making your PDMS devices, that there can be damages to those fragile features. So what tends to be the preferred mold format for hot embossing are going to be monolithic molds. So these could be metallic, glass, or made of epoxy resin. Our top recommended choice for hot embossing is these epoxy resin molds because they have been studied and characterized specifically to withstand high temperatures. So you're going to be able to use them for many cycles without damaging any of the features that are in the mold. And then alternatively, there is etched glass, there are metal molds like aluminum. So these are some of the current options to be able to replicate your microfluidic devices using hot embossing. And here we just have a microscopy image of some micron scale features that were molded into a Flexdym sheet by one of our clients in a recent publication. And just to really highlight to you the ease and the rapidity of the protocol for the molding process, here we have a schematic of a protocol implemented by another one of our clients in a recent publication in Micro Machines. Really what they were trying to make were double chamber organ on a chip devices where you have two Flexdym sheets that are molded and then bound to an intermediate polycarbonate porous membrane in order to culture cells and study cell signaling. And what you can observe is that each step only lasts a matter of a couple of minutes, apart from the last step in which they wanted to bond the device at a faster rate. And here you can apply heat. So they did 80 degrees for 2 hours in order to ensure that the device is properly bonded. But I will go into the different bonding features of the Flexdym just shortly. So Flexdym devices are going to be assembled through a very straightforward bonding process. Essentially, it is through manual lamination. So that means that you're just going to gently and carefully place your Flexdym sheet onto the selected substrate while trying to avoid air bubbles. And this process can then be standardized also using a press. So that allows a way to then for you to really produce these devices more efficiently. But what is really key to understand here is that Flexdym acts as a pressure sensitive adhesive. So you just need to provide this conformal contact and this homogeneous contact throughout the entire surface of the Flexdym sheet with the selected substrate. And if you are, for example, functionalizing your devices, the Flexdym bonding can occur at room temperature. Now, this will take an overnight process, but you have the option of doing this room temperature bonding procedure or accelerating the process by adding heat. And Flexdym can bond to a range of different substrates from different thermoplastics such as COC, polycarbonate, polystyrene, to glass, and it's in Flexdym itself. And so for each of these different substrates, the bonding strength is going to change. And this is why I wanted to highlight this tunable bonding strength of the material. So here we have experimental results from a recent publication which show the fluidic pressures that are withstood for fully Flexdym devices. So you can see those are in blue. Then we have hybrid devices, which are Flexdym on polycarbonate. And finally, devices that are Flexdym polycarbonate and that have been additionally incubated at 37 degrees in order to check for cell culture conditions. And the fluidic pressure was tested for different time periods. So 1 day after fabrication, 1 week, and then 2 weeks. And what you can see is that there is a range in the fluidic pressures are withstood. So for the hybrid membrane that is Flexdym polycarbonate, we're at around just above 1 bar, 1.2, 1.3 bar. And for the fully Flexdym devices, we're closer to 2 bar. So you will see that depending on the substrate that you will use, the fluidic pressures will range from about 700 millibar up to 2 bar, depending as well on the grade and the brand of the substrate material that you will be using. But what is also important to see here is that the bonding strength does not decay over the time period, and that it's also going to be resistant to humidity and cell culture conditions. Another key point is that Flexdym is a recyclable material. What I mean by that is that you can mold the Flexdym using your hot embossing method, assemble your device, use it, and then if you wish to reuse that sheet of molded Flexdym, you can. You simply just have to wash it or sterilize it, which can be done using gamma or ethylene oxide, and then remold your device and create a new device from using the same material. Now here what we have is results from an experiment testing the burst pressure of the Flexdym on Flexdym devices. So these are fully Flexdym devices. And here what the authors did was apply a fluidic pressure to the devices, then wash the material. So they applied the pressure until the device came undone, unbonded, I guess you could say, washed the material and then bonded the sheet back onto the substrate. And what you can see is that the burst pressure withstood does not decrease. It's essentially maintained over 10 washing and rebonding cycles. So this can be also a great advantage of the material. And in addition to this, because Flexdym has a kind of acts as a pressure sensitive adhesive, and because of the way that the polymer chains penetrate into the substrate material, it has reversible bonding. So what that means is that it can have advantages, for the example, in the case of multi-layer designs. So you would like to layer multiple sheets of Flexdym on top of each other. For that process, you have the opportunity to, if you mess up your alignment, try it over again. Because really with, for example, with PDMS or with other thermoplastics, you're only gonna have one chance to assemble that device. And if you misalign, it's gonna go in the bin. So here you have a chance to remove your sheet and then redo the bonding again. And then another key feature of the Flexdym that essentially comes from its elastomeric nature is that it's also going to be a great material to use for valves, such as quake valves and membranes, because it's very elastomeric. And so now I'm going to talk to you more about the biocompatibility and then the biotech applications. So Flexdym has been tested for 2 international biocompatibility standards, ISO and USP. And we have certified that Flexdym is not harmful to the body or to biological in biological studies, and it does not display long-term effects caused by chemicals that leach out of the plastic materials. It's also been tested for irritation, skin sensitization, for systemic toxicity. So in general, it can be used for all of these cell culture, organ on chip, and other biotechnology applications. So talking about that, specifically for the cell culture applications, what essentially is needed in terms of the material that is used is that it is biocompatible. It can withstand strain and mechanical stresses that are physiologically relevant. It has low protein absorption. It displays optical transparency, and the surface treatment is easy to implement. And what we have here on the left are two examples of current or recent publications using Flexdym for perfusion cell culture studies. So in the top, the author did perfusion cell culture of mice dermal cells. And you can see that this is a material that can be easily implemented for this type of application. But what is really interesting is that the author really harnessed the advantage of the reversible bonding. And so we have switching of from closed to open conformations of the devices so that the media can be replenished. And in the bottom, we have an example of the two-chamber device in which two Flexdym sheets that have been molded are separated by a porous commercial polycarbonate membrane. And here the authors used the Flexdym to then culture human fibroblasts. And another key application of the Flexdym is going to be for diagnostics. So here, what we need the material to display is low absorption, for example, to oligonucleotides, nucleic acids that are going to be present in the mixture, to have optical transparency, to maintain a low cost of production, especially in the case of point of care diagnostic cartridges, and to withstand resistance, for example, to fluorinated oils, for example, in the case of digital amplification, droplet microfluidics, and also to show thermal stability for the different thermal cycling steps that are implemented for the activation of the enzymes, usually done in the initial steps of the procedure. So here we have an example where members of our team actually constructed a lab-on-chip device for PCR. And this was done with actually with a previous iteration of the Flexdym. And since then, we have done further optimizations of the material. So it just shows you that this material can be used for these applications as well. So I would just like to finish off by highlighting that the Flexdym is a material that's available on demand. So there is no preempted mixing, degassing steps. It has been designed specifically, and it's really the first of its kind to be designed for biotech applications by experts who have not only the experience in material synthesis and formulation, but that have also already worked on biotech, the development of biotech devices. And it's also a material that has been designed with the idea of creating a compromise between what is needed for researchers in research and development and what is needed in industry. So we're not only going to be trying to improve your user experience in the lab at a daily rate in terms of the speed, the cost, and the practical aspects of the fabrication method, but also we're going to be thinking ahead to what are going to be your industrial needs in the future. So when you want to scale up, you will have the option to do so, and you won't have to switch your materials. And with that said, I would just like to thank everybody for your attention. I'll be happy to take your questions. And yeah, that's it. Thanks.
That was great, Roberta. Thank you very much.
Thank you.